Hey everybody, welcome to episode number 17. It's good to be back. Today is going to be a fun episode. I'm going to be digging into a CVE. We're going to be talking about some exciting news of the week and generally just having a blast with some BPF user space stuff and things like that. So without further ado, if you're in the chat, let me know you're there. I'm happy to raise you up. We got Net Spooky joining us. Good to see you, Net Spooky. We got Noel is hanging out with us. He's also super excited. Noel is generally pretty excited, I would say. Rory is also checking in. Good to see you, Rory. If you say hello in the chat, I'm happy to raise you up, let you know that you're, let you know that I see you and that you're a part of this. It's tremendous. I'm glad you're here. As you can see here on the lower right-hand corner, it says show notes hackmd/@echo-live. If you go there, you'll be able to see the notes for this week and kind of cover what we're going to be talking about. Mr. Eric, good to see you, sir. Always fun. Awesome. All right, well, let's get into it, I suppose. So this week's notes, some exciting headlines. So obviously next week is the Ebpf Summit. If you have not already registered for the Ebpf Summit, you should do that today. Right up here at the top, it'll have a register button. If you go to ebpf.io, where you can find the register button. And when you do click on that register button, it's a free registration. You'll be able to join our Summit Slack and interact with, ask questions of the people who are doing presentations and kind of just generally interact with us. It's a virtual summit. We won't be, this isn't in person for anyone. But the schedule looks really exciting. Some of the folks that are going to be talking are Jana Dogan, Brendan Gregg. Liz Rice is going to be doing a really awesome talk on building a load balancer from scratch, leveraging BPF. Daniel Borkman, one of the awesome kernel developers working with me here at Isovalent. And then Tabitha Sable will be helping us host our Ebpf Capture the Flag, which I think will be super fun. There are a number of really great challenges, and they are Ebpf based, and I think it's going to be a fun one. And then we have Dave Thaler, who has been a guest on eCHO previously. I think it was a few episodes ago. Dave Thaler is responsible for some of the work happening around Ebpf in Windows, which is kind of fascinating stuff. If you want to see more about the schedule before you decide to commit to like registering with the talk, this is basically what's happening. We're going to have a keynote by Thomas Graff talking about the state and future of Ebpf. We're going to have Brendan Gregg doing getting started. We have Jenna. Then we have a bunch of lightning talks, a lot of really good stuff. One of my friends, Jed Salazar, is going to be back doing another presentation. Natalia and Jed are going to be working together, doing a talk on keeping your cluster safe from attacks with Ebpf. Lots of really good stuff. So I'll be co-hosting that with Liz and with Thomas. It's 2 days. It's 9 a.m. I think 9 a.m. to basically 1 on Thursday and Wednesday of next week. So join us if you can. I think it'll be a heck of a lot of fun. Welcome. Russell saying hello. Good to see you. The next thing up is another big announcement on the Isovalent blog post, and actually is being picked up in lots of places, but there is now an Ebpf Foundation. I know that Thomas was working on this really hard for quite some time, and it really finally got announced. So I'm super excited that this is happening. Like Facebook, Google, Isovalent, Microsoft, and Netflix are announcing the Ebpf Foundation. Lots of exciting stuff there. What I really like, I mean, this is a great blog post in general, but I love these XKCD type cartoons that kind of describe like why Ebpf was created. And this is going to be pretty relevant to some of the stuff that we're going to be digging into today. We got John McCabe checking in. Good to see you. Thank you, Noel. And AJ, how's it going? So I like this, it's basically talking about like, if you want the kernel to be more programmable, if you want to be able to do things like observe what system calls an application is making or how long it takes to actually make particular function calls or anything else like that, or if you want to manipulate packet routing, or if you want to do things like this. Like traditionally, some of these features could have been handled by things like a kernel module. In fact, and of course, there's not really a guarantee of safety with a kernel module. So like you write the code, and it's possible that kernel module could actually hang up your Linux kernel and cause a crash. And there's actually an incredible talk that I have linked in the eCHO notes here, written that was presented by Lpe from Facebook, who talks about safe programs, the foundation of Bpf. And if you're interested in that topic, I definitely recommend checking that out, because he really gets into detail about like the trade-offs between like writing a kernel module or writing Bpf, and like why those things are interesting. But heading back to the blog post, I think what's really interesting about this is that it kind of aligns, it lays out a pretty clear story, right? Like as an application developer, I want a feature to observe my application. Hey, kernel developer, please add this feature so I can do the thing. And then, take some time to get something into the kernel, and then it takes some time to get stuff into the distributions that might leverage that kernel. And so the question is like, how much longer, how long does it take to actually get a feature like that developed and pushed? Kernel modules can speed that up a little bit, but it is a challenge for sure. With Bpf, if we're writing some of that functionality in Bpf, we can actually dynamically write that stuff into the kernel. And you can just update to the latest version of that project, rather than having to wait for it to be compiled into the kernel and made it part of that monolithic, incredible Linux kernel that we have. Exciting stuff. So the next thing I have up to talk about, and there's one more thing. I did actually mention this already, but I wanted to make sure I really picked this up, is that the eBpf CTF at the eBpf Summit is going to be hosted by Tabitha Sable, one of my really good friends. So that's actually one of the things, I think probably top 3 or 4 things I'm like super, super excited about the summit coming right up. So if you want to come and play with that stuff, definitely come check it out. One of the other things I found out that is today, GitHub picks today to kill off password authentication for GitHub authentication. Now, most likely, most people aren't hitting this, but if you are using password authentication for Git against GitHub, that'll stop working today. So that's kind of exciting stuff. I imagine there'll probably be some buzz about that happening. Let's get into the CVE and the fix and the research in general, and then we'll get into the blog post. Then we're going to get into the GitHub link. My plan is also to actually bring up a couple of VMs and kind of play with this, get it working, and see what we think. But it's pretty exciting stuff. I've actually learned a lot just in researching this episode. I'm like understanding how to enable user space Bpf and things like this. Oh, that's actually not the right output, but we'll look at that here in just a minute. I don't know why I had that there. But we're going to play with that, and we're going to dig into how this works and like what the actual attack surface is. But first, I kind of wanted to talk about like research in general. I think that this is actually a really great write-up. So this is a blog post that was written by Valentina. She might be joining us in the chat. I'm not sure if she'll be there. But Valentina Pomiotti, known as Champelite, and I think this is an incredible write-up. It does a very good job of explaining kind of their headspace and like how they went about creating this incredible solution, or this incredible way of actually like of exploiting the Linux kernel verifier code to come up with a way to effectively escalate their privilege. And I wanted to kind of talk a little bit about this type of research in general. Like, I think this is super valuable. Two turned. That GitHub change is going to cause thousands of broken builds. Yeah, I know what you mean. Yeah, this is why I was bringing it up, because I think it's like I'm with you, Russell. I think it's going to be super interesting, but we'll see how it shakes out. Over Monday morning. I like that nobody's doing builds over the weekend. That's a solid thing. So I think research like this is super important, and I think it really speaks to kind of like the community aspect of what we're of the Linux kernel and just our community in general, right? Like, this person decided to like dig into eBpf. they found some incredible write-ups on different POCs that did exactly the same thing, or that did similar work in kind of exploring privilege escalation for this stuff, and then wrote an incredible exploit that allows us to kind of walk through how this works. But they didn't just write the exploit and get it out there. They did more than that, right? Like they wrote up a primer on how BPF works. They dug into the actual sanitation mechanism. Like if we talk about eBPF, if you've ever attended a talk on eBPF, one of the things that we spend a lot of time on is the safety of BPF, right? And that is that, like, you can't just write code and inject it into the Linux kernel. That would be probably not, that wouldn't be safe in any way, right? Like if you mismanaged the code that you were actually trying to write, or if you accidentally put it in an infinite loop, if you did any number of different things, if all you had to do was like write that BPF code and inject it into the kernel, that would be like catastrophically bad for the Linux kernel, and there's no way that would probably get in. What this represents instead is you have the ability to write code that would allow for particular events inside the Linux kernel to be hooked. And when an event happens, you have the ability to manipulate or gather context about that event, and then bring that context or manipulation, or bring that context down into user space so you can report on it. And we do a lot of this stuff in Cilium. We also manipulate packets and that sort of stuff. I mean, but there's like a number of different really killer areas that BPF allows us to manipulate and to observe and to do things like performance testing and network manipulation and observability for processes, and like understand which process is opening what network connection, what system calls they're making. You can even use eBPF to effectively write seccomp 2.0, right? You could do a thing where you've written effectively a policy that whenever a particular process makes a particular system call, and leveraging the context that they have, then you could actually immediately reject that process, right? You could shut that process down right at the kernel layer, right? So there's a lot of capability that this expresses, and that's why I think that a lot of people refer to eBPF as superpowers, right? I heard that first from Brendan Gregg, referring to eBPF as superpowers, and I think that that's a perfectly accurate way of describing it. But generally, I mean, more specifically, I should say, when you're writing eBPF code that you're going to inject into the Linux kernel, it has to actually pass the BPF verifier. And the verifier is going to do a number of things. And these things are covered pretty well in this blog post. They talk about Ebpf Maps, which, as I said before, when you're using eBPF to gather context for what's happening at the kernel layer for a particular event, like what process opened a file, whether they opened it or closed it, like all of that sort of rich context can be gathered around hooking a particular set of events, like file open or execve or any of those things. But then once you have that context, how do you express that context down to user space so you can maybe put it into a log file or consume that through some other program? Ebpf maps are that way, right? Like you can actually build an Ebpf map that allows you to basically take the output of what you've, take that context that you've gathered at that process level, push it to a map, and then in the user space, basically pull it off of that map into a file system. The Ebpf verifier does a different thing. The verifier is responsible for making certain that the code that is pushed into the Linux kernel is actually held under a general set of rules, and it calls it out here, right? Like no back edges, no loops, no unreachable instructions, no pointer comparisons can be performed, and only scalar values can be added and subtracted to a pointer. So it's a pretty limited instruction set that has to happen, and that verifier happens after the code is compiled, and it looks kind of at the shape of the program and figures out like what paths are going to be run through this code, and tries to determine that this code will be safe when it is run at runtime. And it does a pretty decent job of that. This blog post goes on to really dig into detail about exactly how the verifier does that work. I mean, and I think one of the things that I was really impressed with was that one of the challenges that Valentini ran into was, how do you go about determining, let's see, where is it at? How do you go about determining how the verifier is going about validating this stuff. Like, it's an incredible read. There's so much good stuff here. Like just debugging, like, kernel level software and like digging into like how these things are actually running. Give me just 1 second to find what I'm looking for here. There we go. So debugging eBpf programs. I think this was actually like one of the things that really sparked my interest in this article as well. So this one, when loading an eBpf program, you have the option to specify a log level or buffer to receive log output from the verifier. So that's super useful for debugging loading failure when the verifier rejects the program. Keep in mind that if you choose to, obviously, I actually really thought this was a great call out, and so I'm going to call it out here explicitly, right? Keep in mind that if you choose to provide a log output buffer, it should be large enough to receive the entire output of that log. If it is not large enough, then loading the program will fail, not because the program is invalid, but because the log overfilled, and you have no way of actually seeing the log that actually caused that thing to fail. So that, I thought that was a really good call out, and I could see, it's like when you read that, you're like, oh man, I could definitely understand how that would burn you. But ran into this in their own debugging, and I could definitely see how that would be super challenging. One of the other pieces that they called out, which I thought was really interesting, was runtime debugging. The verifier log output provides a lot of useful information, particularly when playing with a verifier vulnerability. But being brand new to eBpf, Valentina wanted to get familiar with the eBpf instruction set. They wanted to also be able to look at the values of registers during program runtime, like in a debugger, such as GDB or WinDBG. So when you're injecting bytecode into the kernel, there's a couple of different ways to do it. You can inject already compiled code, or you can inject code that will be just-in-time compiled, and you would basically provide kind of the code, and it would be compiled by Bpf, and then it would be kicked up. And then where that bytecode, if JIT is disabled, the bytecode will be decoded and executed in Bpf core-c. So this is where Valentina really got my interest. I thought this was a great piece of work here. So what they do is they basically compile, they wrote in some print case statements into the code that is doing the decoding. And that way at runtime, they can actually see in the D message what the actual value of those registers are at runtime inside of the Linux kernel, which is a great breakthrough. Like that is like probably I think probably one of the most awesome pieces about this article is like, getting to the point where you're like figure out how to actually understand what's happening at runtime so you can really explore this stuff. Solid work. Solid work. So then they get into the vulnerability piece as well, and I think it calls out the bug and like what the shape of that bug was, which I thought was also pretty fascinating. Wanted to see if we could find the place in the article where this gets called out, because it's like one of those things where I think like anybody would have made this mistake. This is a really, again, calling out like the value of having a community of people who are like looking at this stuff and trying to ensure that it is safe and trying to ensure that it is secure over time is super, super important. And having more people like Valentina out there like looking at this stuff can only improve the security of what we're doing. So this gets into, so there's the range tracking. And we talked about sanitation. And this was all written up by the person who originally found this problem, which is Manfred Paul. He also has a great blog post. I'll link to it here. And it's in the link in the description as well, or in the notes as well. If you want to really, this is where Valentina was like giving a lot of credit to Manfred because of the awesome work that Manfred did to expose this particular issue. And this issue's been solved for some time, right? But we're going to get into that in just a second as we explore this further, but really digs into like the detail of it. So there we go. So the bug is found in the 32-bit tracking information for Bpf and Bpf Aura and Bpf Zor operations. So as shown in the code snippet above, if the lower 32 bits of the bound of source and destination are known, the function skips the 32-bit bounds, right? Assuming the scalar 64-bit max will be called, and it's safe to skip updating the register from the 32-bit. This comment says that the return state is okay because the 64-bit counterpart will take care of it. And it does, except that the thing that it's checking is materially different than the thing that was checked in the 32-bit side. And so that's where the bug happens. And I think that this is like, this is one of those things where you get into it, one of those situations where it will be like super easy for anybody to write this particular type of scenario. I think it's pretty fascinating stuff. Anyway, I think if you want to dig into the real detail, I think this blog post and Manfred's blog post really dig into the detail of this particular thing. And I wish that this was titled Improper eBpf Program Verification in User Space, because I think that's really it expresses what the actual attack surface is. So let's dig into that a little bit more. I'm going to go back to my notes. We talked about the research. We talked a little bit about the CVE. I wanted to pull up the original CVE and show you that. So this is actually calling out the allo32 bug, right? The eBpf allo32 bounds tracking for bitwise and XOR. This is actually the CVE that was credited to Manfred that was originally written up. And the blog post, if you want to read into this particular CVE, this is the one from Manfred, the author of this particular thing. He wrote it as part of a Pond to Own competition, got 30K for it, so awesome work. And then put up a great write-up and a demonstration of how it works. The fix was put up by Daniel Borkman, somebody I work with at Isovalent. So like tremendous that we have like so many incredible eBpf developers who are like very quick to respond on all of this stuff. The fix happened pretty quickly, and it changes the nature of how this testing is done so that we don't run into the same problem. And even in, I wanted to point out that even in this talk, in this document, the great blog post that by Valentina calls out that at the end of their blog post, way down here at the bottom, so the strategy to bypass Alice annotation is excellently described in this blog and also in Manfred's blog. And the details, and here he details the Lpe Exploitation Strategy in Pond to Own. Valentina discovered that there was an integer underflow bug that was calculating the allo limit in the verifier. It was present in March 2021 and fixed in the commit that we were just talking about. And the sanitation instruction patch was patched. So this particular bug is completely patched in the Linux kernel today. And so we have to, and so if we're going to play with the exploit, we have to make sure that we're picking kernels where the exploit still exists. And we'll play with that here live in just a minute. So Alice annotation was rendered completely useless by this bug against exploits of this type. And it went unnoticed, even though many POCs were publicly available. I think that, once it was actually made available, things got fixed up pretty quickly. Of course, the Alice annotation can be easily bypassed regardless. I think this is an interesting point. What they're saying is that, like, if you're in the privileged mode, then you can, then you could exploit it. But if you're in privileged mode, you could exploit lots of things, right? Like if it's one of those things where if you're already in a privileged mode, then you could turn all kinds of features off. But I do think that it's good that it's been fixed, because that way it's been fixed in either case, right? Whether privileged or unprivileged. It's so wild to me that this was not even that this was even noticed. Like, you really have to be reading every single aspect of the code for this, and it's not uncommon bug class for interpreters and parsers. Yeah, I agree with you, NetSpooky. This is like this is like really like the head of the needle kind of thing. That's a great call out. But that's the research life, really getting into the detail. Like another example, like as you pointed out, similar to noticing things like pointer compression in the wild, right? Like that is a very impressive thing. All right, so back to the notes here. We talked about the original CVE. We talked about Manfred's blog. We talked about ALU32 being fixed. One of the other things I wanted to point out, and this actually bridges me into like what I think is the important takeaway of this, right? Which is that like for this hack to work, like for this exploit to work, you have to have particular kernel versions where the exploit still exists. You have to have user space BPF or unprivileged BPF enabled. And I wanted to talk a little bit about what unprivileged BPF is and like why it exists, and then talk about like the fact that you know where you might actually see that enabled in some cases, right? So when BPF was introduced, it runs in like two different modes. You have the ability to do that code injection, where you can write a BPF program that's going to say like look for particular event calls, or try to trace the life of a packet through the Linux kernel, or manipulate the destination IP address or the source IP address. You can do things like NAT. You can do all kinds of interesting things in the Linux kernel with network packets. You have the ability to inject those programs that'll do that, and you can do that as a privileged user. And then there's also the capability to do that same injection as a regular user. Now, this isn't to say that a regular user can inject a code against anything. In fact, it's actually it's significantly constrained. As a user, if user BPF is enabled, which in most distributions it is not, but if it is enabled, then you should really only be able to write programs against processes that are managed by your user. And that's one of the constraints of unprivileged BPF. You'd have the ability to do things like, debug, performance test or profile your application with BPF as a regular user, as long as the process that you're actually going to be doing that tracing on would be something that was specific to that user, like that would be exposed to that user. So if I wrote like, a Go binary, and that Go binary, it would be like, catting an image file every 2 minutes. And I wanted to understand like how many times that function was called. And I wanted to use BPF to understand that rather than instrumenting the code to understand how often that function was called or how much time it took that function to run. If I wanted to just do that generically with BPF, I could do that by leveraging, by writing an eBPF program that would allow us to see how many times that function was called over time, and like throw the counter into a map and evaluate that map to understand like that sort of work, right? But I could only attach that program to a process that was running under my same user. Like I would have to have initiated that process under my UID. If that program was running as a different user, I would not be able to, in unprivileged BPF, write programs that would affect it, unless I had that unless I have some greater level of privilege to actually do that work. This change, which is what I'm highlighting here, there we go. Yeah, is a change that basically makes it so that there's now a kernel config knob for disabling unprivileged BPF by default. By default, it was on, and this change means that now you'll have the ability to basically make it so that whatever distribution you're using has the ability to make it so that unprivileged BPF is off by default. This is certainly the safest way to run BPF inside of the Linux kernel, is like not allowing for unprivileged BPF. And there's a couple of different reasons why that's the safest way. But this article in specific, I think, calls out one of the big ones, right? If you're using unprivileged BPF, you have the ability to inject code into the Linux kernel, and it has to survive all of the constraints defined by not only the LLVM compiler and the BPF verifier and all of those things, but it also has to be only against programs that you run in unprivileged BPF. But, as was described here, there is potential that there could be a bug in that verifier code that allows you to exploit yourself to root. So that exploitation to root would really only work it would only be super valuable if you were running in unprivileged BPF mode. And as I said, in most cases, I would say that How we do this at Isovalent, like whenever you're installing Cilium inside of your cluster, we disable unprivileged Bpf out of hand. Like we disable it on those systems whenever the Cilium agent starts up. It's a system call that we make to disable it. And it's the default in a lot of Linux distributions, I think with the exception of Ubuntu, the default is to run without unprivileged Bpf. And so speaking to NetSpooky's point, like narrowing it down into that one particular space, that's an amazing piece of research. And I think that was a great catch by Chompy and by Manfred to actually catch that particular scenario. Pretty amazing stuff. So this has been fixed. And the next thing I wanted to talk about was getting into, playing with it. So let's play with this thing. Let's get it going. So yeah, I mean, I like doing this stuff live. Let's see. Go 17. So what I've done, like reading the blog post, you can see that there are very specific kernels that this one will hit. And I decided I wanted to see if we could actually get this working. So let's go ahead and give this a try. So up here at the top, oh, it's actually in the GitHub repository. There we go. So this is the GitHub repository where the exploit has been published. And you can see it. And so right here at the top, it calls it out, right? We can validate this against Ubuntu 2010 and Ubuntu 2004, but it has to be a specific range of kernel where we can catch it. And then we can actually trip it up and take a look. So that's what I've got set up here in my environment. Is I've got a Ubuntu 2010 image. Let's get this thing booted up here. And I've already done the work of actually like changing the kernel version. I'll show you how I did that in the next image, but it took me a minute to do that. At first, I was trying to run it against the default kernel that ships with Ubuntu 2010, and that did not work for me at all. So one of the first things we should check is this piece here, which is what I meant to catch in the notes. So I'm just going to update the notes real quick. Mm-hmm. There we go. That's updated. Go back to our terminal. So this line here, if you want to know, like, is this even possible on the Linux systems that I'm using? This is your tests, right? If you do a check for kernel unprivileged Bpfs to CTL and it's set to 0, then this exploit is at least on the table for you. Like, you can at least see if it's possible. Now, the other catch of this is that it has to be a kernel that actually has that allo32 bug in it. And so that was the part that got me. Like, initially, when I ran up 2010, I could see that this was 0. So I was like, okay, it should work. And then I tried to run it and it did not work. And then I realized that I hadn't done this piece, which is basic 58025. Is that the right kernel? I have to change that again. Let's see. In the GitHub repository. Yeah, we're good. 58025. I had to actually install this older kernel and then reconfigure grub to actually pick up that older kernel and then boot to it, and that's what got me there. So now on the binary piece itself, we can actually kind of dig into how it works. And if you want to, and we'll dig into like a little bit more of this in the blog post, but like understanding how this exploit actually works is documented very well in the blog post. Valentina did a tremendous job of writing it up. Move into bin here and do an exploit bin. Here is the output of the exploit on Ubuntu 2010. And it does take a second. While that's happening, why don't we just jump over to the blog post again. And we can look at the exploit code part of it. So triggering the vulnerability. The specifics of this bug were covered in the vulnerabilities section. And here I'll go through how the bytecode triggers the bug. We need 2 registers, 2 tnums in the same state shown in the example. That is 1 register. I'm not going to read all of this, but again, like if you're interested in this is an incredible write-up of like exactly how Valentina wrote this to trigger this particular exploit. Should it? This is the part where I wonder like how people have the patience to write exploits, because like it's sometimes you'll be trying to like reproduce an exploit or reproduce something that you found that actually does allow for privilege escalation or a change in the way that things work. And you'll run the code and you'll be waiting and you'll be waiting. And eventually sometimes it'll hit, sometimes it won't. It's an interesting one. While this is happening, I'm going to bring up another terminal and bring up the other VM. We can look at that one as well. I was playing with this a little bit yesterday, and I wanted to share what I found. Hey, there we go. We got it. All right, so we were the Vagrant user. We ran the exploit bin. It did eventually find the init PID-NS of the stab. It found the credentials, created a cred structure, preparing to overwrite credentials, and then boom, here we are. Who am I? I'm root. So yeah, that is the way the exploit works in live action. That was pretty awesome, and I was actually able to reproduce this in 2104 as well. So I kind of want to jump over there and look at this one. So here we are in 2104. And I decided I wanted to also try and understand like what things can limit the scope of this particular attack in different ways. And so there were a couple of pieces here that I thought were pretty interesting, and I wanted to kind of share them with you in my own looking at this exploit. So in 2104, we have the correct kernel, 5.11.16 kernel, which is called out as one of the viable kernels. Oh, and I was going to show you how I did this in Grub. So I found out about this trick. So when I installed a second kernel, I needed to actually tell Grub to load that second kernel. And because it's not the newest kernel, Grub will almost always default to, this Grub default line would have been 0. And what that means is that the first kernel in the first menu entry in your Grub config will be 0, and Grub will load that first menu entry. And so if I do grep menu entry, boot grub config, you can see the menu entries that are here. This first one would be the one that would get booted by default, which pulls in a 51125. Actually, GNU simple, which is, yeah, it's pulling in a 51125 kernel, which is too new. It's already been fixed. And so that wasn't actually going to allow me to reproduce this particular exploit. Instead, I needed to pick a different one. I needed to pick like a 51116 kernel. And so what I did was I just did an apt-get install of that kernel version. And then I had to reconfigure grub to pick up that version of the kernel that I cared about. And so the way that this works in grub, one way to actually configure it, there's obviously you could deinstall the 51125 kernel, and then the only one remaining would be the 51116. But if you got that wrong, you might be kind of sore about it. One other way that you can do this is through this mechanism. You can overwrite the grub default to follow the menu for you, right? And so basically in this option, if you're looking at the grub menu when it boots up, it'll say advanced menu. That's the option 1 there that I picked. And then which kernel do you want to boot? That's option 2. That picks the kernel that I'm actually loading up. And that gives me the ability to get this working, which is pretty awesome. So let's go ahead and run our exploit again from 2104. And we'll see it work here. But there were a couple other things I thought were interesting because I spent a lot of my time in containerization. So I was wondering, like, is it possible to run this exploit from within a container? So I thought we would try to do that as well. So I'm going to just jump over to a 4th terminal here. Because these are actually running for a little while, I want to 17 Ubuntu 2104 Vagrant up. Nope, it's already up. Vagrant H. Kind get nodes. All right, cool. That is all still running. Nice. So I wanted to show like this and Docker PS. Okay. Yeah. So this is what we're going to play with here in just a minute. So let's jump back over here. Oh, still hasn't hit. So while that's happening, what I wanted to play with was like, would it be possible to run this like leveraging the built-in Docker seccomp stuff? And so to describe this a little bit, to help people understand like what I'm talking about, I'm going to show you the output of a command called captch. This command gives us the ability to understand like what capabilities have been assigned to us as a user, right? And if I do a grep for Bpf, I can see that I have the cat Bpf capability associated with myself. I also have cat perfmon and a number of other capabilities. You don't have captch? Oh, if you don't have captch, you can do apt install libcap to bin. Part of the libcap library. It drops that binary on your system. Okay. What can't you see, Yabez? I'm curious about this. Oh, it's because I had that border up probably. You should be able to see the entire part of my screen. Is that what's happening? Okay. Anyway, so you can see that capability-wise, as just a regular user, I have that capability, cat BFP or Bpf, and I also have cat perfmon. And so as a regular user, I can do this stuff. Now, what I was curious about I know that Docker actually has a bunch of things that it automatically turns off. We call it the Docker default ability to limit the capabilities and the system calls that any given process can run when a containerized process is run. And so I decided to run inside of here and see I'm already root, so I can do apt update. Install libcap to bin. And then we can do capch print grep bpf. I'll do it also without the grep. So in this output, it's a little bit different. My current bounding set does not include Bpf. In fact, it is explicitly denied me. And that's because of the configuration of seccomp that Docker actually runs on any given containerized process by default. Now, inside of Kubernetes, it's a little bit different, and we're going to get to that here in a second. But inside of Docker, if you're running with the Docker defaults of seccomp, then this process will likely not run. But let's try it out, right? Let's prove that. And it's V. Oh, that didn't work. Oh, that's because it's the wrong place. Docker run this V. And we're inside of our container. And then I wanted to run that same binary that we had already. Oh, actually, before we do that, let's go ahead and do our sysctl command. -a grep bpf. We can see the same sysctl. This sysctl is not namespaced. It's kernel level, right? So we can see the same output here, which I thought was interesting. And then we can go ahead and run our exploit. And it says nope. And the reason it says nope is because of I installed it in the other container. But it's because I have Bpf explicitly denied me inside of the scope of this container. So if you're running with the Docker defaults for security, then you're not going to have this won't be exploitable, even if it were available on the underlying node, which I thought was actually pretty neat. So do we have an exploit on the node yet? We do. Well, on this one. Hey, it worked. So on 2104, with the right kernel, you can exploit this. You can exploit bin. But even on that same node, what I was doing was running a Docker container to see if we could exploit it inside of a Docker container, and that is not possible because Bpf was denied me, right? When I bring up a Docker container, even though I'm running as root, like the way that Docker automatically configures this stuff, it disables it. And if you want to know more about like how like the defaults of that stuff work, I did a talk on this at San Diego KubeCon last year, talking about seccomp profiles and how seccomp profiles work and like what you can do. But since Bpf is blacklisted, sysbpf is blacklisted at the by Docker when spinning up a container, it's not possible in there. Now, even more interesting, is it possible to do inside of Kubernetes? And so what I've decided to do was I brought up a kind container, get clusters, So I have one kind cluster running. It's just got a single node on it. And if we do kubectl get pods, we can see I have 2 pods running here. Scribe pod bash. Now, this is a security thing that Kubernetes is constantly improving on, but it does actually represent an interesting challenge, right? So inside of kind, we're actually running containerd inside of kind. So out here I have Docker. Out here on the node, I have Docker. I can see Docker PS. And then if I do Docker exec into kind node, I don't have Docker, but I do have containerd, right? And so I do have like TLS. So I do have containerd running inside of Docker, and at the end of the day, this is still just a process running against the same shared Linux kernel that I have in the outside node process, right? So when I start a container process inside of containerd, inside of a kind node, that's still just going to be another PID on the outside of that Docker container at the end of the day, right? But what I thought was interesting was this. So if I do kubectl exec ti bash. Oh, it's been restarted. Okay. Kubectl cp exploit bin bash exploit temp exploit bin. Okay, now I can do kubectl exec ti bash. And that gets me back into my container. And then there, it's the exploit. Does it run? Yes, it does. So Kubernetes, by default, does not use the same seccomp limitations that Docker does. To enable those limitations, what you'd have to do is you'd want to go ahead and enable the Docker defaults. And if you're curious about how to do that, if enabled, the kubelet will use runtime default seccomp profile by default, which is defined by the container runtime. So this is what I was referring to before, right? If you're actually leveraging if you pass a feature gate to Kubernetes, to the kubelet, and this is what I mean by we're constantly improving this stuff. So in Kubernetes 1.22, you now have an alpha flag that you could actually configure on the kubelet itself that tells it to use the seccomp default of whatever the container runtime is, right? Right now, by default, that is not the case. By default, we actually have a very different capability output inside of a container than we do if we actually if we're running with the Docker defaults. So seccomp is the way of actually limiting those system calls that can be made. So I wanted to show you what that would look like real quick, because I've actually just brought up a thing that we haven't really spoken of. So let me just jump back over here real quick. We'll do kubectl exec back into that pod. We'll do apk add libcap. Oh, I already have it. I might. Nope. So apt update. Apt install libcap to bin. Now I'm running inside of that bash container that I showed you earlier. That's running inside of a Kubernetes cluster, inside of kind, like capch print bpf. Did I do a run here? Oh, it didn't work. Never mind. So it did start up, but it didn't run. And I was like, why is it actually even trying, though? So that's an interesting one. Because cat BPF is disabled, you would think that that would not even start. So that's an interesting bug. It's like the actual limitation. Oh, you know what it is? Do I have cap sysadmin? Neat that it actually started. That'll be a fun one to look into later. But it didn't run, so we were still in our situation where even though it did actually start, we weren't able to get an exploit inside of the running container. So pods inside of a kind node or running in container D, even with the default capabilities, don't allow us to actually exploit this vulnerability. So I thought that was pretty interesting stuff. All right. Any questions that I can answer for any of you? Do you have anything that you would like to share, or any ideas that you'd like to express, or anything else like that? I'm happy to talk about those things, but we're coming right up at the top of the hour. Let me know if this was a useful episode. It was a fun one for me to do. Oh, how was it found? I didn't find it. So the way I'm kind of speaking for Valentina here, but Valentina writes up exactly how this was found and how they decided to research it right here in this article. So if you want to check that out, definitely check it out. Yeah, great questions, Aptum. Valentina is ChompyLeet on Twitter, and I hope that everybody has a great time. Remember, next week, Wednesday and Thursday, eBpf Summit. Go register. Come do the CTF with us. I'm really looking forward to seeing you there, and I hope that everything is great with you over the weekend. And I'll see you again in 2 weeks when I do this. When I do the next episode of eCHO. Next week, I think it's Liz, and I'm not sure if it's active or not, because I believe it is. Yeah, I believe next week is Liz, and it'll be a good one. So thank you, AJ. Thank you, Noel. Thank you, Rashran. Thank you, Mythos. Thank you, NetSpooky. Thank you, everyone, and I will see you all in 2 weeks. Have a great weekend. And yeah, keep the research going. I just love this stuff. Talk to you later. It was great. Bye.